Okay, thank you. First of all, let me thank the organizers for the opportunity to talk. And I'd like to present a mini review of hairy black holes, of all known solutions. Well, if it's possible. So more precisely, I'd like to discuss first the no-hair conjecture. Then, well, these titles, 20th century and 21st century, this sounds a bit stupid, but in fact, this more or less reflects the situation with hairy black holes, because in the last century, people mainly discussed hairy black holes with non-abelian gauge fields. And in the current century, they study black holes in modified gravity theories, and this is related to what Gary was talking about. And finally, I will say some words about the current status of the conjecture. First of all, what is the conjecture? In 1969, Ruffini and Wheeler said that all stationary black holes which exist in nature should be completely characterized by their mass, angular momentum, and electric charge. And these parameters can be observed seen from infinity in the form of fluxes. So you measure the flux, and you see the flux, and you measure the charge. And they also stated that black holes cannot have any other external parameters not related to the Gauss law. So if such parameters existed, they would be called hair, such independent parameters. And so Ruffini and Wheeler stated that black holes could not have hair. Now, what is the logic behind the conjecture? The logic is actually quite simple. They say that in nature, we observe many conservation laws which can be violated. For example, in normal conditions under room temperature, the chemical content of matter, which means the molecular structure, is preserved. However, if you burn something, then there is a chemical reaction which destroys molecules. So, which means that when the temperature gets higher, this conservation law is violated. Now, the atomic structure is usually preserved, but if you consider the atomic bomb explosion, then atoms get destroyed. Well, the baryon number is preserved, but then they say that in extreme conditions, for example, in the center of neutron stars and so on, baryon number can change. Now, well, okay, so let's, okay, fine. And black holes are formed as a result of gravitational collapse. And the collapse is really extreme example of a physical process, which is so violent that it breaks everything apart from very few conservation laws which are related to exact symmetries of the Lagrangian. As, for example, the local Lorentz symmetry or local U1 symmetry. And associated to the symmetries, there are gauge fields, massless gauge fields. And these gauge fields, these parameters cannot be absorbed and swallowed by a black hole, and they remain attached to a black hole as parameters. And then they can be measured from infinity as Gaussian fluxes. So this was the logic. Therefore, a black hole, when it forms, it forgets everything. All information is lost, apart from these three numbers, M, J, and Q. So essentially, the statement is that black holes are very simple objects. They are characterized by only three parameters. And then if you have two black holes with exactly the same values of M, J, and Q, these two black holes are identically the same, identically. There's no difference between them whatsoever. So all history of their formation is forgotten. Well, at the time of Ruffini and Wheeler in 1969, the only black holes which were known are Kerr-Newman black holes. So these are black holes obtained in the electrovacuum theory when you solve Einstein equations with the electromagnetic energy momentum tensor. And these black holes are characterized precisely by three parameters, M, J, and Q. Next, there was a chain of uniqueness theorems within the electrovacuum theory. Theorems initiated by Werner Israel, then Brendan Carter, and others, Mazur, and others. And so the upshot was this. So within electrovacuum theory, the most general black hole solution with a non-degenerate event horizon must belong to the Kerr-Newman family. So again, these black holes are characterized by three parameters only. And therefore, the conjecture was actually proven within electrovacuum theory. Fine. But then, of course, nobody claims that all physics should be described by Einstein-Maxwell theory, because there are other fields in the world, and they may or may not give rise to other black holes. And so, conjecture actually does not say that all black holes should be definitely described only by Kerr-Newman. And we know nowadays that there are theories in which Kerr-Newman solution is not a solution. So there are theories where black holes are different. But the conjecture tells that all black holes, whatever they are, should be completely characterized by Gaussian fluxes. So this is the statement. Now, if one considers other theories, suppose one takes other physical field denoted by phi. Phi can be scalar, vector, tensor field, or whatever you like. And then the field equations schematically look like that. So there are Einstein equations and the matter equations. Now, one cannot say immediately if there are black holes or not. So now the conjecture tells that black holes should be either Kerr-Newman or something different, but still characterized by Gauss law, or no solutions at all. Unfortunately, one has to prove this conjecture case to case. For each individual particular matter model, one has to analyze this system of differential equations to see if there is something or there is nothing. And this activity was initiated by Chase, Teitelboim, and most notably by Bekenstein, who managed to prove a series of so-called no-hair theorems. So what they did was to take for phi a field, for example, in the simplest case, a scalar field. Then it turns out that there is a simple procedure. For example, you multiply the scalar field, the matter equation, by phi, then you integrate by parts, and then if a field is bounded at the horizon, you can drop the boundary term, and what remains is a positive definite term, which should be zero according to equations of motion, to the equation of motion, and therefore the field should be zero. Now, but assuming that you can drop the boundary term. But sometimes boundary term is important, but only in the case where a field is unbounded at the horizon. Therefore, the conclusion is that either you get solutions with unbounded phi, which are not interesting, or you get solutions with trivial phi, and solutions with trivial phi are usual ordinary black holes. And in this fashion, the absence of non-trivial black hole solutions in this system was proven for a number of physical fields. As for example, for scalar fields with various potentials, for spinor. Oh, okay. This must be this. Sorry. Sorry. Okay. So what's happening? Oops. Okay. For spinor fields, for massive vector fields, and for other fields. So there is and then everybody believed for a long time that no High conjecture was true. The first embarrassing example, sorry, oops, I have to do this, was found in the context of the theory with conformally coupled scalar field. So there is a usual scalar field, but then there is a term which Gary didn't like. He said immediately that it should be excluded. And then in this theory, one finds exact black hole solution whose metric is extreme Reisser-Nordström, and the scalar field does not vanish. So it actually diverges at the horizon. Well, first people didn't know what to do with it, but then they noticed that, well, this solution contains only one parameter. It's a mass. And the mass is measurable from infinity as a Gaussian flux. And scalar does not have independent parameters on its own. So in this case, it's called not hair, but a secondary hair. So there is following terminology. So therefore, they say this solution does not violate the no-High conjecture because this black hole solution is completely characterized by the corresponding charge. Well, the first, yes?
If you do a conformal transformation,
yeah.
say like the equations are standardized equations, you get Einstein.
Right, but
then the metric
is not a block. No. Then you get this Fisher and another. So actually,
okay.
how the solution was constructed by Bekenstein. He took this solution, known solution, made a conformal transformation. Yeah. Well, entropy, it's extreme solutions. So entropy is, entropy is finite. The temperature is 0. Phi is divergent. Well, what can one do? Well, but there is this R here. Because for extreme Reisser-Nordström, R vanishes because it's a trace of the energy momentum tensor and it's 0. You see. Okay. Now, the first example of solution of black holes which are not of Kerr-Newman type was found by Gary Gibbons in the context of so-called dilaton gravity. So this is a theory which contains electromagnetic fields and the scalar field, which couples to F mu in the following way. So it's a dilaton field. And then the theory contains very simple exact solutions, and which are not Kerr-Newman. So Kerr-Newman is not a solution in this theory. So solutions are given in this, described by the simple formulas, and then they describe static spherically symmetric and asymptotically fluxed black hole with a magnetic charge. Well, one can also add electric charge if one wants. And so the independent parameters of the solutions are mass and the magnetic charge. And again, scalar field has no independent parameter. So it is again not a hair, it's only a secondary hair. So the conclusion is that no hair conjecture still holds. Now, the first real evidence against the conjecture was obtained by Lecoq and Moss, but only on perturbative level. So they considered so-called Skier model, which is very popular in UK. So this is a theory of three real scalar fields, which combine in the following way to form a unitary matrix. And then the Lagrangian is this. There is something like a vector field, but it's not vector field, it's a composite vector field. And then there is a gravitational coupling here. And now if coupling is very small, then one can expect the scalar fields to fulfill equations on a fixed Schwarzschild background. So one can expect that the back reaction can be neglected in this way. And Lecoq and Moss analyzed these equations and indeed found a globally regular solution for not one, but infinite number of different solutions for phi, parameterized by a topological charge. So in Skier model, there is a topological charge. So this originally this was introduced by Skier as a model of baryons, and there is a charge which is associated to mappings of S3 to S3, and it can be interpreted as a topological charge. And so this was what they found. And so therefore, such solutions can be considered as perturbative approximation for hairy black holes in the limit where the back reaction is negligible. But for some reason, this result remained more or less unknown because it's only perturbative analysis. And Lecoq also produced non-perturbative solutions, but published these solutions only in proceedings of some obscure conference. And so this work is essentially remained unknown for many, many years. Now, the first example of hairy black holes, which really became widely known and recognized, and which was reproduced by many authors, was obtained in the context of Einstein-Young-Mills theory. So here you take Einstein gravity and couple and add the Young-Mills field, non-abelian gauge field, for the gauge group SU2. And in this case, so the field tensor is a nonlinear function of field potentials. So there are three potentials. So the index A takes values 1 to 3. So there is a usual linear piece on nonlinear one. And in some sense, it was natural to expect something in this theory because again, the conjecture emphasizes the importance of local symmetries. And this is also local symmetry. It's not an abelian theory, it's non-abelian, but it's local. And associated to this local SU2 gauge invariance, there are non-abelian gauge fields. They are massless, and so one can expect to find something. And then the procedure is as follows. One makes a static spherically symmetric ansatz for fields. So in this case, the metric is parameterized by two functions sigma and n, and then the gauge field is chosen in the following way. There are simple differential equations, and then one requires the solution to have an event horizon at some point where this n vanishes. Then one integrates this, unfortunately, only numerically. So there are no analytic solutions in this case. And then one finds asymptotically flat solutions with a regular horizon and with a non-trivial gauge field. But But this gauge field is such that its field strength decays as 1 over cube, and therefore the corresponding charge is 0. However, the field is non-trivial, and in fact, this amplitude W oscillates, and it can oscillate once, twice, 3 times, and the number of oscillations is a free parameter. So therefore, the solutions are characterized by their mass, which is measurable at infinity, and by a number of oscillations, which is not measurable. So it's, and if mass is given, there are infinite number of different black hole solutions with different number of oscillations. So all of them have different geometry and different Young-Mills field. And so therefore, this is really a primary hair, which manifestly violates their conjecture. So this result was actually obtained in my PhD many years ago, and then it was published, and it was almost immediately confirmed by other groups. And as soon as this was known, well, this, in a sense, triggered the whole avalanche of similar discoveries. First of all, people managed to generalize these solutions to static but not spherical symmetry case. They found stationary generalizations. And then many other similar systems were discovered. So in particular, it turns out that one can add to Einstein-Young-Mills other fields, in the simplest case, Higgs field. And the Higgs field phi can be, for example, in fundamental representation or in triplet representation. And depending on this, the theory admits different classical solutions. So if for example, phi is in that joint, then the solutions of theory without gravity are 't Hooft-Polyakov monopoles. Now, if you switch the gravity on, then you get 't Hooft-Polyakov monopoles a little bit deformed by self-gravity. But most important that you find also solutions where there are 't Hooft-Polyakov monopoles containing a tiny black hole in its center. So technically, you change the boundary conditions at the center. Instead of regular origin, you require the existence of event horizon at some finite and small distance from I equals to 0. Yeah. And then what you get is 't Hooft-Polyakov monopole and a small black hole inside. And the same works for other solutions. And then, interesting effect, when you increase the value of the event horizon, the black hole first still continues to support non-trivial hair, but then starting from some critical size, it swallows all the hair, and it becomes Schwarzschild. So therefore, hairy black holes in this case can exist, but they should be sufficiently small. Well, then in other cases, people studied non-abelian version of the Einstein dilaton. Then this Einstein-Skir model was studied really in great detail. There are many branches of solutions, and everything is very extensive. Has been extensively studied. Then people studied solutions with Gauss-Bonnet term, and then with this cosmological term, and so on and so on. And so here is the summary of some properties of these solutions found in the last century. So these hairy black holes, static or stationary, arise generically in systems containing non-abelian gauge fields coupled to gravity.
You call it hair even if it is a consequence of non-abelian gauge fields?
I call it I call it hair whenever these solutions carry additional parameter not associated to the Gaussian flux. As for example, this number of oscillations. Number of oscillations is not visible from infinity as a Gaussian integral, but it is a parameter. And so we have mass, and for a given value of mass, we have many different black holes. So view from far away, they're all identical. When you approach the horizon, you see the difference. This is the hair. Say it again. Yes. Right. The simplest, you enlarge the gauge group from SU2 to SU3, for example. Yeah, but for example, well, and then you have a non-abelian, non-trivial Cartan subalgebra, and so you have, and if the field belongs to this, it's equivalent to U1. And in this case, there are solutions. Yeah. So yes. Yeah. Supersymmetric solutions without horizon, I know, but with the horizon, I don't. I can't say immediately. Extremal. Yeah, you're right. This is the activity of Ortin and company. Yeah.
That's the recent stuff.
Yes.
I just wonder whether there was older stuff.
But then we have to be ADS. This is gauge.
It's not. The SU2 is not.
Oh, it's different.
So now these solutions can have in addition scalar fields Higgs or dilaton and or curvature corrections. Can be static but not necessarily spherically symmetric. This is interesting because the non-abelian gauge field carries spin and also isospin. And there are superpositions of spin and isospin such that the result can be either like that, then it's spherically symmetric, or it's like that. And then it's only axially symmetric, even though it's static. Static but not spherically symmetric. Then there are also spinning solutions, but also there are funny cases. In particular, there are situations where the horizon rotates, but the angular momentum is zero. Yeah. So there is something distributed in between. Well, so most of these solutions are unstable, I must say, but not all of them. So for example, gravitating monopoles are stable, even though complete stability analysis has not been checked. But most dangerous instabilities are absent. So now, typically, so these solutions can be either of arbitrary size, black holes, as in the pure Young-Mills theory, or there is a upper bound, and if the upper bound is reached, then the black hole loses its hair and becomes structured. In the opposite limit, where the horizon shrinks to zero, one would say that nothing should remain, but it's not true. So if the horizon shrinks, what one gets is a regular gravitating soliton. Is a kind of a lump of bound state over non-abelian fields on the space-time geometry. So it's some sorts of couple systems. Yeah. And so all this was summarized in our report paper, physics reports. It was quite some time ago. So, but this was the 20th century. Now, what is happening now in the 21st century? This. People are currently anxious about the fact that our universe is accelerating. And this is what Gary mentioned in his talk. So assuming that Einstein equations hold, this acceleration can be explained by introducing a term into the right-hand side, a dark energy term. So assuming that there is some stuff, dark energy, which fills everything and accounts for the acceleration. Well, many people say that it is dark energy is simply a cosmological constant, and that's it, and which agrees very well with the observations. But other people are unhappy with this. They say, well, it's difficult to explain the value of this term and the origin of this term. So let's rather assume that it's a dynamical field. There is something. Or let us assume that Einstein equations are not valid in the infrared regime. And then there are many theories on the market, many theories in which one modifies gravity or where one introduces new degrees of freedom. Typically, this just additional scalar field. And as Gary said, typically in these theories, well, authors of these theories, they're usually not physicists, they are astronomers or whatever. They don't care about stability, positivity of energy. They say that energy can be negative. It should be, the solution can be ghost or poltergeist, or depending on how you call it. And but if you violate the standard energy conditions, then you violate the conditions of applicability of no-hair theorems. And if these conditions do not apply anymore, you can try to construct new black holes. And this is what people do. So everybody is now happy. Nobody cares about positivity or stability. People just construct hairy black holes. And then, well, and then there are models with a scalar field. And the simplest thing what people do, they violate the strong energy condition. So if you take the standard Lagrangian with a real scalar field, then one can prove that if the theorem is static and spherically symmetric, and if the potential is positive, then the only solutions are Schwarzschild. Phi must be constant. So this is the theory due to Heusler. Therefore, if you want to get something, you should abandon the condition of positivity of V of phi. And this is what people do. So some people do it honestly. They choose some V, which is not positive definite, and solve differential equations and construct really find hairy black holes. But most people prefer to proceed in the other way around. So they prefer to adjust the potential in such a way that the field equations are fulfilled. And everybody is happy. And here is the example of such a solution, first found by Bronnikov, I believe. And then the potential is this. And so this is a very simple solution, and it is static and spherically symmetric and asymptotically flat. Exact. Now, and there is quite an activity along this direction, but for the reason I honestly do not understand. In all cases, the potential is essentially either exactly the same or a version of this. So for some reason, people who do this, they end up with more or less the same result. This is interesting. So I didn't check why they always get. But then there are many generalizations because you can add extra fields, so it's vector fields, and then you can make a scalar complex and so on and so forth. And so there are many publications. Now, some people prefer to violate not the strong but also the weak energy condition, which means to make the kinetic energy also negative. And then there are some black holes in this case. Well, but what is interesting, it's not enough to have only this negative. You also should make V negative in order to get black holes. But this system is mainly interested in the connection with the wormholes mentioned by Gary. So in particular, if you, so this again, this is a poltergeist field. But if you set V to 0, then there is a very simple exact solution describing a wormhole wormhole because the radial coordinate r changes from -infinity to +infinity. And in both limits, you get a flat space. Whereas when r is equal to 0, you get a sphere of a minimal radius mu. And therefore, these two asymptotically flat regimes are connected by a throat of the radius mu. And then there are geodesics which pass through the throat, interpolating between two regimes. So this is a wormhole. So I will say some words about wormholes. But this is also quite an activity nowadays. Now, this result, so these results are a bit pathological in my opinion, but the next result is really physical and very interesting, I think. So people, Herdeira and Rado, they did the following thing. They consider gravity coupled to ordinary complex scalar field, massive complex scalar field, nothing else, very simple system. Now, in this case, there is an O'Hare theorem due to Penn and Sudarsky, which says that if the system is static and spherically symmetric, there is nothing. Now, what Herdeira and Rado did was to abandon the staticity condition. And the crucial observation is this. So if you take the Kerr metric, then on the Kerr background, there are bound states for field phi, which have a spinning phase. So there is omega and also m. And omega should be just at the threshold of superradiant instability. So these solutions were found by Hort in the extreme Kerr analytically, and then they were generalized to all values of angular momentum numerically by Herdeira and Rado. And so again, there are bound states on the Kerr background, neglecting the back reaction. And this suggests that you can use these solutions as you can generalize them to fully back-reacting solutions when you switch the back reaction. So first, the back reaction is small. You start from bound states, and then you start to increase in the back reaction, to increase the gravitational coupling, and do the numerical iterations. And this gives a fully back-reacting gravitating solutions with non-trivial hair. So the metric is, well, it's in the standard form, and there are functions which depend on r and theta. And so here are some properties of these solutions. So the solutions carry mass and angular momentum, and the charge of field phi, but it's not a local charge, it's a global matter charge. It cannot be expressed by flux integral, but only by a volume integral. Solutions do not have static limit. This is interesting. So if you take G to 0, then at some point the hair is lost. They become just vacuum solutions. Now, if the scalar charge is taken to 0, when it becomes very small, the solution reduced to these scalar clouds. Now, the solutions can be super rotating. So for Kerr black hole, G ranges from 0 to m squared. So for these solutions, one can have G which is larger than m squared. And finally, if one takes the limit where the event horizon shrinks to 0, then you get, then one gets a globally regular solutions described as spinning boson stars. So actually known for many years. So boson stars are bound states, self-gravitating lumps made of scalar field with spinning phase. So this was known. And so now these are static limits, these are horizonless limits of of this solution. So I think this result is really excellent, and then they generalized it in many ways. This is now, there is quite an activity, so they are now considering complex vector field and so on and so forth, and each time it works. And so they, Herderi and Radu, already managed to get many new solutions. Well, Q balls, it's essentially spinning boson stars. Well, for Q balls in flat space, you need a potential. In curved space, you need nothing. You can just do, without potential, it works. Yeah. Now,
So you can have a massive scale, a complex massive scale?
no, massive.
So that's the potential.
It's essential. So some mass is needed. Without mass, it doesn't work.
Right, but that's a potential.
But it's positive.
Okay, positive.
It's positive, yeah. So energy conditions are okay. All of them are okay.
Can you couple the gauge B?
Yes. Well, as I said, what they are doing now, they are generalizing in all possible ways. There are plenty of generalizations. Yeah. Now, another theory, well, this is what was also mentioned by Gary, and this is, I think, is quite serious. This is a theory of Hordensky. So this is, so again, when you consider gravity coupled to a scalar field, you can ask, what is the most general theory of this type? And the answer was obtained by Hordensky in 1974, who was a student of Lovelock. And he discovered that the most general theory with the second order equations of motion, not higher, second, is this. So the Lagrangian is the sum of 4 pieces, and each piece contains an arbitrary function of the field phi and of square root of its gradient. And so you see there is a huge freedom. You can take whatever you like. And all previously considered theories with gauge fields, with scalar field, such as scalar tensor model, f of gravity, quintessence, chi-essence, you name it, whatever. So everything is contained here, everything. So this is really the most general theory. And then theory contains, shows effects, well, is non-minimally coupled. For example, there are terms like that when the F5 is directly related to Einstein tensor. So all this violates equivalence principle. And now one can expect many black holes in this case, but surprisingly so far not much has been found, because people were mainly interested in the case where the theory exhibits so-called shift symmetry. And this only happens where these functions do not depend on phi. They depend only on x. But this symmetry allows one to rewrite the scalar field equations as a divergence of a Noether current. And this helps a lot. But then, first of all, it was shown a no-go result was presented in this case. So the idea is essentially this. If the metric is static and spherically symmetric, then the current has only one component, JR, and then it turns out that then the equations of motion are this. Therefore, GR has to have this structure where C is an integration constant. And if C does not vanish, then the norm of the current diverges at the horizon. Therefore, C must be 0. But if C is 0, then the current is 0 everywhere. And if current is 0 everywhere, then in the simplest case, assuming that phi prime enters the Lagrangian quadratically, one has the following condition. And the function f typically approaches a constant at infinity for asymptotically flat solutions. Therefore, the conclusion is that phi prime should be 0. And this is a no-go result. So this was proven by these people. But then other people described loopholes in this proof. And they were so happy to find these loopholes that everybody now gives citations of this article, and even though the article is wrong, it receives many citations because people are now happily constructing hairy black holes due to these loopholes. And so the first loophole is that it is possible that phi prime enters Lagrangian only in a linear fashion. And then the current has the following structure, and if it vanishes, it does not mean that phi prime is 0. And then the theory contains a Gauss-Bonnet term, linearly multiplied by phi. And then there are solutions constructed by Soteriou and Zhu, but these are very similar to solutions constructed in the context of Gauss-Bonnet dilaton gravity, almost one-to-one. The only difference is there is exponent of 2 phi and just phi here. Otherwise, it's the same. So this is nice, but well, not really new, in my opinion. Then a lot has been done to study this particular subcase. So again, one takes the generic Hordensky, and one chooses the functions in such a way that the theory boils down to this. There is an Einstein-Hilbert term, and then there is a Einstein tensor and the metric, and so which modify the kinetic term of the scalar field, and there is lambda. Now, the model is interesting in one respect. It admits flat space solution for any value of lambda. You take whatever lambda, and then flat space passes through. And then people say that this is very nice because this is so, in a sense, solves the cosmological constant problem. Because in this problem, one has to explain the value of lambda. In this case, there is no need. Whatever lambda is, you have flat space. It's OK. Yeah. Then there are black holes. They are, well, they're interesting. For the solutions, 5 has a time-dependent piece. But their metric is not very interesting. So it's just a Schwarzschild metric, even though the phi has a non-trivial structure. So this was discovered by Babichev and Charmozy. But unfortunately, solutions of this type and all their generalizations are unstable. Then people again studied this model. And I must say that the model is completely integrable. This is another interest of this model. So field equations in this case reduce to a cubic algebraic equation. As soon as you know solutions, you know everything. So in particular, there are black holes, which are not asymptotically flat. Also, many people study them, but then the problem is that phi prime squared contains h. And h is a metric function which changes sign at the horizon. And therefore, phi is bound to become complex valued somewhere, either inside the black hole or outside black hole, depending on the. And this is also not a very nice property.
Does this mean it's just above, guys? I mean, in your kinetic energy.
No, it's for anything.
Phi is pure imaginary.
Okay. So eta is epsilon divided by sigma. Well, depending on poltergeist or not, it becomes imaginary either inside or outside, but somewhere. Yeah. Okay. Then people studied other models. Well, in particular, they considered terms with a higher order curvature term, series with higher order curvature terms in the action, in quadratic, so as Gauss-Bonnet gravity, or conformal gravity, which I should mention because Chris Pope is in the audience. They did it with in the conformal gravity, and there are black holes constructed, I would say, in the quite usual way. One has to integrate numerically, but then everything works. Yeah. Well, there are also Harawa-Lifshitz, but let me skip this. And then the last topic I would like to mention is massive gravity, and I was personally involved into this, and this is quite interesting. Yeah. So massive gravity is is a theory which was introduced in 1939 by Fierce and Pauli. And then it has interesting history, because many times people thought that the theory was unphysical and it should be abandoned, that it's dead. So, for example, there was a famous story of discontinuity. People discovered that if you take the graviton mass to 0, you do not get back general relativity. You get theory which gives different predictions. This is so-called VDVZ discontinuity. Then other people discovered that this problem can be solved if you go to nonlinear regime where so-called Weinstein mechanism applies. But then theory was almost killed by observation of Bulwer and Desermate in 1972, who noticed that the theory propagates not 5 degrees of freedom, as would be okay for the massive graviton, but 6 degrees of freedom. And then the 6th additional one is poltergeist. Okay. And then they said that this was really generic conclusion, and then the theory should be definitely abandoned. And nobody dared to object against the authority of Stanley Deser until 2010, when the group of Daram, Gebadadze, and Tolle discovered that the argument can be circumvented. And so essentially the idea is this. So what is massive gravity? Massive gravity is a usual Einstein-Hilbert term plus the potential term for the metric. This is a scalar function, u, which depends on the metric. Now, if you take just metric, the only scalar you can construct from it is a trace of the metric. So G mu contracted. But it's just a number, not very interesting. Therefore, if you want to get something else, you need another metric. You need 2 metrics. And this is the called bimetric theory. And then in the simplest case, you choose the second metric to be flat, whereas the first metric to be dynamical. And then one can construct, one can consider the tensor and consider all possible traces and traces of powers. Then you take arbitrary function of it, fix the coefficients in such a way that the theory has a correct Fierce-Pauli limit, and then you're done. You have infinitely many theories. All of them has correct Fierce-Pauli, but unfortunately, all of them also have the Bulwer-Deser problem. Now, what these people discovered was that there is unique choice of the function u for which the ghost disappears. And this is unique up to 1, 2, 3, 5 parameters b. And then the potential is expressed in terms of eigenvalues of the matrix, which is a square root of G inverse times F. And the square root of the matrix is a matrix whose square is this argument. So now this theory, and there is now the whole activity in this business. There are the whole industry. But the theory is still under the severe criticism of Stanley Deser, who is still active. And then he says that, well, he almost succeeded to bury the theory in 1972, but then some people exhumated it, and then one has to bury it again. And then he uses arguments mentioned by Gary, because the theory has 2 metrics and therefore 2 light cones. And these light cones are not necessarily the same. And then he did some analysis of characteristic surfaces and then discovered that, well, light cones can be oriented in the wrong way, such that there are superluminal signals, even though this is not for all solutions, but for some of them. And so he says that, well, the theory is bad, it should be abandoned. And many people who worked in this theory, they actually quit the field because of this. But there are some tough guys who still continue. And then interesting generalization was obtained by Hassan and Rosen. Well, essentially, you can make both metrics dynamical. Not only one of them, but both of them are dynamical. And then the potential is the same. And then one can study black hole solutions. And, well, this is biometric theory. In the simplest case, you can choose the two metrics to be proportional. And then the field equations tell that lambda should be a constant, and it should fulfill a fourth-order algebraic equation. And then the equations reduce to solutions with a cosmological constant, which can be positive or negative or zero, depending on the root. And then, therefore, you get just standard solutions, standard black holes, S and GR, but with a small difference. GR black holes are stable, whereas these black holes are shown to possess a small instability, mild instability, which grows proportionally to m, and m is supposed to be a small, very small parameter. Then other solutions, well, it's quite interesting. So the two energy momentum tensors have the following structure, and then there is the tensor tau, and if it vanishes, the equations are split into two groups, and each has its own cosmological constant. And then you can independently solve, and to obtain a solution which is black hole in one sector and black hole in the other sector, and the masses of the black holes are arbitrary. So the event horizon can be completely different. They should not coincide, and the temperature can be different. This is the case mentioned by Gary. Even though the coordinates should be related by the following differential equations. And then there are also hairy black holes where the two metrics are both diagonal, and in this case, one finds that black holes should be common for both metrics, and then the surface gravity and the temperature should be the same. So there are some numerical solutions. And finally, there are also wormholes. Well, because wormholes need for their existence violation of the null energy condition. And in bigravity, the two energy momentum tensor can have arbitrary structure. So they do not a priori fulfill any conditions. And then if you do, you find indeed wormholes, actually many times, many types. So finally, one concludes that if bigravity indeed applies, then the black holes are almost the same as in GR up to the small correction in the vicinity of the horizon. And then there are also hairy black holes. And finally, the conclusion. In view of all this variety of hairy black hole solutions, one can ask the question, is there still any sense in no hair? Well, I think, yes, surprisingly, the answer is yes. First, no hair applies for real astrophysical black holes, simply because the microscopic world is described by Einstein-Maxwell theory. But the conjecture is proven inside Einstein-Maxwell theory. Now, if you go to the microscopic regime, you can get other solutions, other hairy black holes, but they're typically very small. And when they grow, they lose their hair. They become bald. Well, if there is a cosmic scalar field, something which describes the dark energy, there might be other black holes, but up to now, there are no stable examples. There are some solutions, but they are really, really ugly or unstable. And if massive gravity applies, then the solutions are all the same as in GR up to a very narrow region in the vicinity of black hole horizon, where there is accretion of massive modes to the black hole. And therefore, it seems that astrophysically relevant solutions indeed satisfy the conjecture. Thanks.